Okay, today we're talking about the ATXMEGA, which, if you remember from our description last time, is like a shark with laser beams. Before we do that, we want to talk about, very briefly, about fuses, because we kind of forgot to cover this topic. So fuses are basically little configuration options on your microcontroller. They're things like, they tell the microcontroller whether its clock source is internal or whether it's using an external oscillator. One of the fuses is called CKDIV8, and it's turned on by default, and it makes the clock, it basically divides the system clock by 8. So if you think you're running at 8 megahertz, if this box is checked, you're actually running at 1 megahertz. And the funny thing is, you probably won't notice this for a while you're writing test code, but then suddenly you'll have like an LED soft PWM function, and your LEDs will blink because they're actually being updated 8 times as slow as you expect. So we're going to send instructions for how to reset or how to set fuses. It's kind of a dangerous operation to do it within WinAVR and with AVRDude, because you can you're basically setting all the fuses at once, and if you have one hex bit, set incorrectly, you might basically break your chip. You will set a configuration option that your gadget doesn't like. So the safer way to do it is to, if you're using Windows, is to get AVR Studio, and there's a graphical interface for checking and unchecking fuses so that you know what you're checking. And if you don't want to download that, just come to office hours, and I think a TA will probably be able to set your fuses in about 5 seconds. It's a very fast operation. So that's the safest way is just to get it done in office hours.
Basically, on your chips, when he's saying you can brick it, what he means is you might have said, oh, clock div by 8, you could check it, uncheck it. That doesn't break anything. What can break it is if there's a thing where you can use the reset pin on the ATXMEGA as an extra I/O pin. But once you do that, you can't reprogram it by toggling the reset line low anymore. So if you're making like a million of something and you've got your code down cold, no problem, get that extra pin. But if you're writing code and you accidentally change that reset line, you can no longer reset your gadget to reprogram it, which is bad. The other one that you can do is you can disable, I think, SPI programming, which means you can no longer reprogramming it using the ISP that you guys all have.
Or you can decide that your clock source is external. So because it's not on your mini gadget, you don't have an external clock. If you set it to be external, your microcontroller has no clock anymore. Without a clock, nothing runs. So.
And more importantly, the ISP requires
a clock
on the microcontroller to operate.
So you can't reprogram it either.
Yeah, well you can, but you have to hook up a function generator, generate a clock on some external pin, and then you can bootstrap it to where you can reprogram it, and then you take away the function generator. It's usually faster to just desolder the reset microcontroller, throw it on the floor, and put a new one on. So feel free to reprogram your own fuses, but you need to do it safely. Otherwise, you'll have to visit TTAs and get a new AT10.
All right, so yeah, sorry about not talking about that extensively in the past.
Although, honestly, usually all we would do is people would test their gadget and be like, okay, the power's on. They would come to one of our laptops. We'd wave our hands over the fuses and then say, here you go, your fuses are good to go.
Yes. If you remember the mini gadget construction, we actually did do that. Probably most of you don't remember that step. We basically did it at the same time that we programmed on the initial code to make the LED. All right, so that's fuses. Let's talk about XMegas and Tinies. All right, so here's the comparison between a relatively small XMega chip and the Tiny 84. So flash memory, 8K and 32K, which isn't that much of a difference, except this is the variant of of the Tiny series that has the most flash memory, and the XMegas can go up to 256K or more.
That is the smallest XMega and the largest AT Tiny.
So RAM also.
RAM on the XMega, they go to 16 or 32.
Maybe even more exciting, ADC, 2 megasamples per second at 12 bits versus 15 kilosamples per second at 10 bits. Now, why do you care about that? If you want to read like speech, you generally have to sample at 40 kilohertz, 44 kilohertz, it's like CD quality. So you can't do it on the Tiny. It's not possible. On an ATXMEGA, it's not even hard.
The ATXMEGA also has DAC, so it can do digital to analog. So after you've read in your sound, you can then play sound output to a speaker. Like you can do real audio, whatever you want.
Not just buzzers.
The timers, the AT-Tiny has 2 timers. One's kind of crappy, one's also kind of crappy. The ATXMEGA has 5 timers. I think it even has more than that. Like it just leaks timers everywhere.
Yeah.
And then the Tiny, there's one UART sort of, kind of does some stuff. The ATXMEGA actually has 7 USARTs, 5 of which can be used for SPI. There's 2 I2C. If you want to talk to like 11 different digital contraptions, the ATXMEGA works. The AT-Tiny does not work nearly as well.
DMA, we'll talk about that in more detail about what it is. There are no DMA channels on a Tiny. There are 2 on an ATXMEGA. This means that you can, without involving your microcontrollers, basically the core computer of the microcontroller, you can sort of shift data from one input or output to another input or output without taking up clock cycles or CPU cycles. The Tiny can run at 16 megahertz. The ATXMEGA can run at 32 megahertz. Notice though that they run at a lower voltage. You cannot power an ATXMEGA off of 5 volts. You have to do 3.3 volts or less. And that's generally just a trend in all sorts of processors. A lot of CPUs and computers you can only power at like 1.8 volts or even 1 volt because lower voltage, if you remember, basically equates to lower power use.
And modern CPUs are still burning ridiculous amounts of power. The only thing I'll add here, so what this is showing you is 8-bit microcontrollers. This is basically,
both of them are still 8-bit microcontrollers.
It's still, you're writing the same sort of code. You're not doing anything too crazy. As soon as you start saying, I want something bigger and faster and better, you start talking about the ARM core processors, Cortex M3, Cortex M4, ARM7, ARM9. And they have similar features to the ATXMEGA, except then the clock rates just go through the roof. They have way more DMA. Interestingly, they don't have more UARTs. Like this is actually a very good feature set in terms of like twiddling things in the real world.
Which is why the ATXMEGA is good if you want to control a bunch of real-world applications. Like if you want to communicate with sensors or do control speakers or motors.
Yeah, but you still want to stay in a simple kind of processor. Because as soon as you go to an ARM7 and a Cortex M3 and 4, you start saying, should I be running an operating system? And if you've taken that class, there's details in running your own operating system. And even if you're going to take somebody else's operating system that works on those chips, there are a lot of frustrating details with getting that stuff working, which is completely different. Yes, you still make program and make compile, but like the things that are happening in that make file are much more complicated than what happens in like your AT-Tiny example code. So when something goes wrong, it's much easier to fix this, especially if you just want to make some money.
I guess one last note, obviously there's more pins, but there are variants of the ATXMEGAs that also just have native USB device capability. So they would be, you just hook up the USB data transmission lines from a computer and it talks over USB native.
Yes, but again, you start writing your own USB control.
Yeah, it's a fair amount of code to get USB right. That said, there are simple ways to handle USB, like the cable that you all got with the nice 4 pins is just a USB. It contains a USB to serial converter, so you can actually talk over USB with it to any device that has TTL serial, which is almost anything. Even the AT-Tiny has to show you the older things. Okay, so that's ATXMEGA versus Tiny. And like Brian was saying, there are 32-bit controllers that are even more advanced that you'll find in cell phones or Raspberry Pis, but then you start running operating systems and the code gets quite a bit more complex. The tool chains of code.
So, and what you'll find is you don't get more UARTs, you get fewer timers, you get fewer DACs, fewer agencies as you start to get into these bigger processors. So if you have to actually run like software to like process your audio and process your data, that's what you use those for. But you still actually end up using these kind of processors to do your low-level interfacing. Even the Raspberry Pi, if you look at it, nobody actually uses the low-level I/O on it. They go buy these breakout boards or daughter boards that if you look on them, they're either an Arduino or an ATXMEGA, an ATXMEGA, right? Everyone avoids doing that at the computer level.
Okay, so the XMEGA series is a little bit more complicated, and what Atmel has done to maybe declutter their data sheets is they've created two different types of data sheets. They've created a part-specific data sheet and a manual. So the way that the part-specific data sheet is, it tells you exactly, so there are a number of XMEGA A series or D series or whatever series chips. The part-specific data sheet will tell you, let's see if I can get this.
And for some reason, Atmel has completely revamped their data sheet style in the last week.
Really?
Yeah. You'll see in a second.
All right, computer, oh, okay.
Across the streams. But basically, the part-specific, yeah, it will tell you if this is the data sheet for the ATXMEGA 32A4. Here are all the pins. It has this super important page called the pin map page, which tells you what goes where. And then if you actually look at like, what does the serial section do? It just says, hey, it's got serial. You should probably look at the real data sheet to figure out how it works. And then what you do is you go over to the A series manual, and inside that it has what you're normally used to seeing, where it's like the long explanations about the serial, and then finally at the bottom, here's the register description, here's all the registers, here's what you do with them. That's all in the A series manual, whereas the part-specific one, it tells you exactly where the pins go, what's in the chip, but nothing about how to use it.
So the A series manual generally, so the part-specific manual is useful when you're doing your circuit board schematic and layout for the most part, and then the A series manual is more useful when you're doing the actual programming. Now you need both at both times, but just in terms of how long you'll be staring at each one. When you're programming, you'll mostly be staring at the manual.
Basically, when programming, you will say, okay, I hooked up this accelerometer to this SPI port. It's on pins PA3 and PA4 and PA5. Which one is that? And then you go to the pin map, you say, oh, that was SPI2. So then you go to your code and you just, everything is about SPI2. And that's the only time you need to print. All right, that's still angry?
I don't know, I think this, is this, it, or is this
Looks
somebody
like
else's?
this.
Yeah, this is it. I had it open. PowerPoint's still angry, but whatever. So this is the part-specific data sheet.
And
It's
they now
a
look
mere
different, but don't worry about it.
108 pages. That's the other tip-off. If it's only 108 pages, it's not giving you all the information you need. And I'm serious about that. So yeah, you can.
Do you want to show the pin map that's like this?
Yeah.
I think it's way down at the bottom. Pin out and pin function. The only thing you need in this data sheet is a couple pages down in section 30. Alternate pin functions, yes. So here they define stuff, and like the DAC pin is the DAC.
And here.
Ta-da. So when you want to use analog to digital converters, you have to go here and you say, aha, ADC0.
It's on PA0.
Yeah, which is
pin 40.
So PA0 to PA7 are ADC ports, but then you got bonus ones on PB0, PB1, PB2, and PB3. And you just have to look there to figure out where all your stuff is.
Yeah. So yeah, that's.
And then like here's a serial port, TX and RX on USART0 on PC Scribble and BC Scribble. I can't read that, so I doubt you guys can either. But it tells you where the pins are.
C1, yeah. Let's see.
And
if
that's
I
just
still
where you
remember
need to be. All right. You trying to look changed everything.
Here it is. Okay, so here's the preliminary manual. It's 432 pages. I'm going to download that.
And for some
Oh.
reason, they
Whoa.
changed the font with a few other things.
All right.
But it's the same data sheet.
As long as they only change the width.
Oh, yeah.
So recommended reading, notice this, the device data sheets and also the application notes, which we're going to get into later. Those are going to be very important if you want to program, if you want to quickly program stuff. They basically tell you how to do a lot of stuff. So, okay.
So then other details, the XMegas are only 3.3 to 1.8 volt parts. So you cannot use 5 volts. So some of you ended up having like sharp IR sensors that need
Yeah.
5 volts. So then suddenly you have to worry about how to interface between different voltage levels. There are really handy chips that let you just do this step pretty easily, but it's more work than just, whereas with some of you guys we said, hey, you're running with this 5 volt accessories, just run your processor at 5 volts, easy. Or, oh, you have a 3 volt accessory, just run your part at 3 volts. And like, you don't have to worry about interfacing between them because you just make them compatible. Nowadays, it's very easy to find 3.3 volt equivalents for most things. If you have a data sheet for a part that looks like somebody photocopied it, that's like 2 degrees off, that means you're using a really old part, and it's probably going to be annoying to interface with. Just go look for one that has a nice data sheet that was generated, this millennium. And then these arbitrary parts, we used to say they had a ton of terrible errata because like a lot of things didn't quite work right on the XMegas, but actually now they kind of do,
Yeah.
as long as you buy the newer ones. And now they have USB, which is fairly new, a couple of years, I guess.
No, the XMEGA series is 4 years old, I think, is when they first came out. So
Yeah.
that's starting to be mature, I guess. Although the ATXMEGA series is about probably 12, 13 years old. So. All right, so how do you program these? Basically, you're using the same tool chain as the AT Tiny. The XMEGA 32A4 is even still supported in WinAVR, even though that was released almost 3 years ago. Some of the other ones, I think, some of the newer ones, you may have to use Atmel's own compiler.
So what actually happened, all of you guys are using AVR GCC and AVR libc. There used to be some guys who basically made this thing called WinAVR, or whenever, if you believe their thing where you have to say it that way. And it was just, open source tools. They would just keep it up to date and output it for people who were using Windows. And then what happened is like 2011 was the last year you could ever get a new version. And what actually happened is I think Atmel basically hired all those guys away. And now Atmel Studio 5, Atmel Studio 6, you can download them from Atmel. Buried way deep inside is the actual what it does, and it's now called AVR GCC Toolchain for Windows. It's snuck, hidden away in the install directory, the 1 gigabyte monstrosity of AVR Studio. So if you still want to use it, you still can. You just have to install AVR Studio and then change the path from WinAVR to AVR Studio / AVR GCC toolchain for Windows, and it's all the same stuff as there. And the reason you need to do that is because a 3 or 4 year old compiler does not have chips that are younger than 3 or 4 years. And frequently people find you want to use the new chip and not the oldest, crappiest chip you can find. Or if you're in Linux, you can just get the newest versions of AVR GCC and AVR toolchain. Frequently they are not whatever package you can get through a package manager. Usually those are out of date as well. But this stuff exists. You can also use Cygwin and like that. But they're very different syntax. You don't use the _BB anymore. And now what it is they have a whole bunch of things. So when they want a BB, which just creates a bit mask, they now just have a thing called pin1 _BM, and you get a pin1 bit mask, which looks like a 1 and a whole bunch of zeros, whereas the pin7 bit mask is a whole bunch of zeros and then a 1. So that you have a lot less of these weirdo macros in your code. There's also a bit position where the pin 3 underscore BP would be the value 3, so that when they needed to do some shifting in your code, they'd use the bit position. And then there's a group configuration where when you guys look, if you remember like setting the clock select lines for your software PWM, they had 3 pins, they had a big table explaining that you could get clock divided anywhere from 1, 8, 64, 256, 512, but you had to select these 3 bits in various sequences. Most of you just used the biggest one because we told you to. But if you actually wanted to do that, your choices in your code was to either have something that looks like random register or equals bit value, clock select 1, 0, clock select 1, 1, clock select 1, 2, and it just kind of looks ugly. Whereas with this, you could just say random register or equals clock div 0 underscore GC. And then that's your div 0, or you can have div 1024, div 8, and it's a lot more readable for people who are trying to figure out what you're doing with these little twiggly bits.
Yeah, so although it's different, it's actually better. The register setting stuff is clear. It's generally a little bit more sane. I wouldn't say it's as clear as the Arduino yet. It's definitely better than the AT.
And then you guys, I don't think, at least in this class, we haven't made you write enough code to get angry at how everything is so specific, where you're like, okay, now I have to take this other port and set these pins to outputs, and then these data direction lines high. Whereas they finally have structs. So there is port A, there's a port object, and you can initialize a port, and if you want another port initialized the same way, you can pass a reference to that port and do the same thing. If you have 3 USARTs that you all want configured to be 9600 baud serial, you can have one function that initializes a serial port struct. So like it's more, real programming as opposed to, if you look at an ATXMEGA, some of them will have 4 serial ports, but all they do is they have different enumerated macros, and you literally have to make 4 init functions with different named registers and macros just to get them all initialized to do the exact same thing. So your code just looks horrendous. So it's a lot nicer on these XMegas. And there's a bajillion of these defined. They're all hidden away. I think this is actually in our project, somewhere in like the course documents we have this, because it's a pain to find.
Yeah, that's true.
Because all of these pin group configurations, bit positions, bit masks, there's a sensible naming scheme to them, but you have to learn what the sensible naming scheme is.
The easiest way to do it is just to look through that clear file.
Yeah.
Okay. So the tables for each module are in the parts data sheet. So we just showed you this within the data sheet. So you know that like pin D, if you look at this, pin D2 has a bunch of interrupts. It has a timer, timer zeros on it. I think a USART, the RX pin on a USART. So you kind of get a sense of like what's going on each thing. So like Brian was saying, you can see there's a USART D0 and a USART D1. That basically means there's a serial port on port D, and there's actually 2 of them. There's serial port 0 and serial port 1. And what's nice is like your code for USART D0 can work with USART D1 without needing to make a whole new function. Okay, ports, are a little bit more complicated in the sense that each I/O pin now has a bunch of different configuration options. And this is actually a good thing. So most of you used like a pull-up resistor on your button to pull it down or pull it up. With the XMEGA, there are built-in pull-down, pull-up resistors, so you can choose to either have it pulled up by default, pulled down by default. You can obviously set the data direction to output or input. You can set and clear them. I think you can
invert the bit. If you decide that in your world, when you say 1 to the port, you'd better turn your LED on, but your LED's wired backwards, so you have to actually give it a 0. You can set the port as inverted, so that when you give it a 1, that pin goes low and your LED turns on.
Right.
Um,
There are interrupts on every port, there's interrupt levels.
Yeah, there's all kinds of just sort of crazy things. You may not need them. But what they also did is they created a bunch of identical registers that do very similar things. So for instance, there's a DIR register, which is exactly the same as your data direction register. It tells you the data direction registers. If you write to that, like you did the DDR, it'll do the same thing. But they also created DIR set, DIR clear, and DIR toggle, which also have 8 pins in them. And if you wanted to, instead of looking at your data direction for the, you could simply say, I'm going to toggle pin 7. I don't care what it is, I'm just going to toggle it. It's going to be the opposite of what it was. And you could totally do that using code, right? You could read the data direction line for that pin, and then figure out what its value is and then set it to the opposite. Or you can do complicated stuff where you read it, mask it, clear it all in one instruction. Or you can just toggle it. Or if you just want to clear it or set it, right, you can explicitly set pins. And you end up with a lot less of that weird port and equals tilde port or equals blah, blah, blah. And you could just say, DIR clear, this pin, done. And there's a lot less shenanigans. So it just looks like better code. It looks more like code and less like squirrely Qbert angry geese.
So is it, DIR A for port A or out A for port A? It's not exactly like that. There are these registers, port A out, port A DIR, but you shouldn't use them. Instead, what you should do is access them via the start name. So port A has, just basically a bunch of different registers associated with it, including a direction register, a DIR set, a DIR clear, an out set, out clear. And so you access stuff by typing basically port A dot here. And then let's see, find it easier to just get to this. Or maybe,
Yeah.
all right.
Well, we can just show it real quick. So I realize not everyone's going to be using an ATXMEGA, so most of you will be like, I don't care about this. I'm not going to get tested on it, so relax. The code. So you guys had to do exactly this. You had to have your set output sort of business with the set LED. Now you can just say, oh, port, set it out as an output. Otherwise, set it as a clear it. Right? It's a lot cleaner looking. When you're doing really complicated stuff, it's nice that all the pieces are much simpler looking.
And notice what is being sent to this is a reference to port A. So, this is a little bit of pointer and direction, but basically this becomes the same as port A dot here set equals pin 3 underscore BN.
And so for those of you who are really looking forward to doing much more complicated software, like this looks a lot more like real people software. You don't have to constantly be doing little macros. And you want to set the direction output. This will work on all ports, right? You don't need to write another function to do it.
Yeah, that's a big thing in ATMEGA. If you want to make a general set output function, it's a very complicated function because you have to just.
There's 3 or 4 registers you have to hard define. Oh, it's the LED pin. Oh, we also have to define the LED port. Oh, and the LED DDR. Yeah. And sometimes the LED pin, the pin of the port in register.
So clocks.
So it has a 2 megahertz internal clock. So if you do nothing, it's just going to run at 2 megahertz. But it also has a phase lock loop, and it can go up to 16 times faster. Or if you want to go some other random speed, you can do that too. 16 megahertz is great if you're going to do USB stuff. But basically this function does some magic poking and just turns on the 32 megahertz oscillator and lets you run at 32 megahertz instead. And so what's kind of interesting is that you start up at 2 megahertz and then you're allowed to boot yourself up to 32 megahertz. And then at any time you could go back down to 2 megahertz. You could go even slower if you wanted. So you have a lot more power control over your system. So if you're doing a lot of computation, you go into hyper mode, you hit the turbo button, and start doing all kinds of stuff very quickly. And then when you're done and it's time to sleep, you could either go to sleep, or you just clock yourself down to like 128 kilohertz and just chill out and wait until something happens.
There's also a built-in real-time clock. I think it's some ATXMEGAs, which is basically like a,
That's all of them.
yeah, it's a quarter crystal type, right?
Well,
It's
so
active.
there's a terrible RTC, but it's approximately 32 kilohertz. But what it means is that you could have this time, and then you could have like your other time. So you could have like a slow timer that's just counting up milliseconds. And it's a millisecond plus or minus a little, but you could start building like a timer and start having like more operating system like stuff that are helpful. Like it's nice to say, well, I had a timeout, and this timeout is based on time and not like 32 megahertz time. Like no one cares about that. You care about did something happen within a second. If not, we do something else. And then there's also, if you're doing high-speed PWM, it actually can overclock, and you can do up to 128 megahertz. And the reason for that is that sounds really fast, but let's say you wanted to have 16-bit control. So take 128 megahertz and then divide it by 2 to the 16, and then you're left with, I think, 60 kilohertz? I don't remember, but it's not as fast as it sounds. So if you want to have really good control over something going a few hundred kilohertz or 50 kilohertz, does anyone have Google? What is the answer to
I
that?
think 2,000.
It's only 2 kilohertz? That's got to be faster.
2,060.
Well, anyway, it sounds fast, but it's not. Okay, well that's depressing.
But if you want 10-bit control.
If you want 10-bit control, you
So yeah, just to be clear, this is not the speed at which your CPU is processing things. So you can't overclock it to 128 megahertz and calculate, add or subtract at 128 megahertz.
You can just blink
You
LEDs
can blink
at up to
LEDs.
128 megahertz.
Exactly.
Or more likely, you will twiddle pins on a motor controller and get 16-bit control, speed control at 2 kilohertz, or you might get, at 20 kilohertz, you might get like 12-bit control or 11-bit control, which is still pretty good.
All right, so interrupts are pretty much the same as before. Like what we've told you about interrupts and what they do, basically comes over to this. There are far more ways to interrupt things. Like all these peripherals have different ways of interrupting stuff. You still write an ISR, they still queue, but now you actually have 3 levels. So you can have a low-level interrupt, which interrupts your code, but a high-level interrupt can interrupt it. So it's just sort of priority, like the high-level interrupt will always interrupt the lower-level interrupts and not the other way around,
So
which can be useful.
Yeah, one good example is, let's say you're doing really fast serial communications, and so you make that a high priority, so as soon as that serial byte gets in, you do something with it so that when the next byte comes in, you're not going to overflow and lose information. Whereas your low-level interrupt might be your soft PWM to blinky LEDs, where it's going at about 120 hertz, and if it gets delayed a little bit, nobody cares. And then there's also interrupt behavior where you can end up with starvation and interrupts. It's probably not way beyond the scope of this class, but you can fiddle with some other stuff.
Okay, you get a DAC, which is not a misspelling of an ADC, it's digital to analog. So precisely like an analog to digital turns an analog voltage into digital bits that you can read in. This turns a register setting into an analog voltage, and it can do that at up to 1 megasamples per second and 12 bits, so very fast. So you can turn your gadget into a signal generator, like the benchtop signal generators you might find in an electrical engineering classroom. Or you can record speech with ADC and then play it back with the DAC. You would hook this up to a speaker amplifier and drive a speaker, and it would play sound. And if you also hooked up an SD card, you could record gigabytes of sound and play it back, and now you've got an MP3 player. So yeah, there's lots of stuff you can do with this. Any other uses for DAC?
Voltage references for feedback loops.
All right.
Somebody wanted to have a voltage controlled oscillator, there you go, that's your variable voltage.
Yep.
That's very convenient. Okay, so DMA, this is a feature that you don't really ever find on an 8-bit microcontroller. Anyone who does a lot of like electronics, computer engineering stuff already knows what DMA is, but basically it's direct memory access. It's, let's say the most common stuff where it starts happening is when you've got a lot of data and you just need to put it somewhere else. So you say, I've got this audio file, I want to put it out on my DAC. If you were writing code that did that, you'd say, okay, it's now time to put the next voltage in my output buffer. Let me go read the next byte in the buffer, set the DAC to that value, and then I'm going to go do something else. But oh, it's now time to do the next one. So it's very CPU intensive, and so like it takes forever. And so what DMA lets you do is just say, hey, Mr. Memory Controller, please take, at some fixed rate, take the data from this bucket and put it over here. And that's all it does. It just does this in the background while the CPU is busy, adding up numbers, subtracting numbers, jumping around in code. The data is just going where you want it. And basically, you have data, it's either an SRAM, it could be another one. You could take the data from an ADC and have it just slurped by the DMA and put it to RAM, so you could look at it later. So you could say, hey, have you captured 6,000 samples yet? And the DMA says, sure I have. Here's your 6,000 samples. Then you do something with them, and then you start the DMA up again. You could have a serial port that data goes somewhere, or the serial comes from one serial port, and then you put it on your USB port, and you're acting as like a serial to USB bridge for some device. And this is where you basically start doing stuff, because generally, as long as you're only doing one thing on your microcontroller, you use the CPU, everything works great. When you want to do two things on the microcontroller, usually you use the interrupts, and if you're lucky, you don't hit 100% CPU utilization and everything works great. But when you start trying to do more things, DMA makes your life much better. So any like real processor has DMA. Nowadays, like they do stuff where they just sort of preemptively fetch things in ways I don't even understand anymore.
I mean, basically, if you think of like, say you are sampling analog at 2 megasamples a second, that's a lot of samples. Your clock speed is 32 megahertz maximum. So you have 16 clock cycles in between each sample. And if you're trying to process any of that data in real time, you're just not going to be able to do it. So, you use DMA, you can take 10,000 samples really fast, store them into some sort of memory, and then take them out of that and do like a Fourier transform or something on them so that you analyze the data in some way, not in real time. So this is a way of basically, it allows the microcontroller to
Be very
do things
efficient.
very quickly and efficiently, and possibly do things in bursts where it can't necessarily process everything, but you want some sort of something to happen very quickly. So cue it for later.
And this is like a good example is how good is your sound card in your laptop. It's either completely done in software or it's done via hardware using DMA. And you're either, your sound gets funky when your computer gets loaded, or your sound always sounds fine. Maybe this is like 15 years ago and nobody noticed this
Still happens.
But yeah.
All right, so in addition to DMA, there are things that are called events, which are kind of similar to interrupts. But they're interrupts basically for DMA. Like an event might trigger a DMA, might trigger a memory access to start transferring. Or an event might be, I'm done transferring. I've got to 6,000 samples and you told me to stop at 6,000.
Programmable trigger might be a good
Yeah.
name for an event. So great examples of what you do is you set up a timer to overflow. So let's say you want to sample something at exactly 8 kilohertz, which if you've done like a digital sampling class, that's usually when they start you off as 8 kilohertz sampling. So you say, okay, my timer's going to flow at 8 kilohertz. And then you create an event that says, when this thing overflows, the ADC should start and convert. And so you could then, and then the CPU wakes up when the ADC is done. So every 8 kilohertz, an ADC sample is just magically starting. And like, that sounds useful as opposed to like just starting whenever it feels like, or trying to figure out like, okay, I'm just gonna constantly sample and then guess which one is the one I want. Or you might want to have your UART captures data from the GPS, and then you want an SPI to write it to the SD card. But you know, you can do these very complicated things. So UART gets data, DMA slurps it away based on that event, and then the SPI, it gets data, so then it automatically sends it to SD, and then when needed, the CPU can wake up to like do a page write or page load or whatever it has to be. So suddenly this stuff gets very fast, and then your code can be furiously working hard on blinking lights to make cool colors or whatever your code has to be doing. Whereas like the hard work is being done automatically.
So application notes. If you go to the product card, so each of these have like a...
Yeah, so do you see how tall that page is? Like that scroll bar, we're kind of at the top of the page. Here's the data sheet. What's all this stuff? And it just keeps going and going and going. And what ATMEL does is, for some reason, they really want people to use their chips, so they try to make it as easy as possible. And what they do is they give you some things. So like, hey, would you like to use the DMA controller? Here's an application note. And what they actually do is there's a PDF that explains what's happening, and then there's a little zip file where they give you code that just compiles on an XMEGA and does exactly what they tell you it does. So like the ADC, you want to just find one for like ADC?
Yeah, so
or iSquared C.
Here's the DMA.
I think
that you
iSquared,
use.
something that's like more sensible.
Well, how about serial? We're going to use that.
Yeah, serial is good.
So,
You want to search for serial? There are a lot of them.
yeah, so basically you may have to do something like this. Serial, and I don't want serial memories. I want XMEGA USART.
XMEGA USART. So would you like code that just makes your ATXMEGA USART work?
All right.
Answer is probably yes.
So in here they have 3 ways of using a USART, serial port. One is through polling, so you're basically, your CPU in your main loop, you're saying, hey, have I got something yet? Have I got a character on my serial port yet? If so, do something. Yeah, question?
I have one note about this sample code though. I was using it a few months ago, and one thing I learned is that a lot of the sample code is written for, I believe, the Intel compiler for the AVR, which is an expensive compiler, and it won't necessarily work with AVR GCC.
Usually,
There's this AVR compiler.h file that if
Okay.
you include it, it seems to work.
yeah, you include it and it munges the mungy bits.
Okay. There was one that I found for an AT-Tiny that I couldn't get to.
Depends on how old the code is too. Their XMEGA stuff is all pretty new and good.
Okay.
Their ATMEGA stuff
Yeah.
is not as good.
That's totally true.
Probably one.
Now, I guess what we're also telling you is that for Gadget 2, you're welcome to go find drivers and use them in your code. We're more interested in gadgets than making you guys poke all the registers from scratch again. So, go ahead and find things like, these USART drivers. What I'll tell you is that they're usually pretty mediocre in terms of implementation, but they work. And sometimes a mediocre implementation you don't have to put any effort into.
Oh, yeah.
That can be nice.
Most of the time.
They're not efficient in any way.
Yeah.
But if you say, gee, I really want to save some bytes to EEPROM and then load them up later, like you can do that. It's it's the same kind of register poking. You'll end up with a couple functions with a couple lines of code. Or you can just go find the EEPROM driver for XMEGA and you're done.
Or you can take the EEPROM driver, take the parts you want, maybe change the code a little bit to make it more efficient, and you're done.
Yeah, and
You don't have to start from scratch.
And I'm pretty sure, I don't know a specific one, but like all these example code probably works, but you may still have to understand what's going on, figure out why it doesn't work in your case.
And I mean,
Maybe a configuration, maybe a buggy example.
for understanding what's going on, obviously each zip file comes with a PDF.
Yeah.
So
I would read the PDF first and then figure out what to do. It turns out that ATMEL has a lot of these. They have for XMEGA, they may have them for Tiny and Mega, but maybe not. I'm not sure. Just trust
I
them.
wouldn't trust, yeah. So yeah, I mean, they're giving you like example code for how to use the serial port, not just with polling, but also if you want to use it with interrupts instead, or if you want to use EMA to, take the serial data and just quickly shuffle it somewhere. So there's a bunch of approaches basically to how you read data from a serial port, and which one you do is pretty much whatever is appropriate for your application. So yeah, the app notes are very, very useful. They are sort of, in Arduino land, like Prost was showing, they have all these, fairly nicely laid out functions all ready for you. So you have just your put byte and get byte or whatever, and it's done. The app notes are
Basically.
kind of analogous, but definitely hairier and not as easy to work with because they're not just integrated into the compiler. You don't just have immediate access, you have to include the file.
But what you'll see there is right away they give you, with the Arduino, you get to use the polling-based approach for serial. That's what you get. Whereas AppNow said, well, here's the polling approach. It's kind of terrible, but it's the easiest way to understand the code. Oh, by the way, here's the interrupt-based one that will automatically fill a buffer for you. And oh, in case you want that buffer to be filled with no CPU intervention, here's the right way, the DMA approach. So like they're giving you the various sophisticated ways, and then you can integrate them into your setup. Whereas Arduino, right, it works right off the bat, but then does not work any better, put more effort into it.
All right. So reference schematics. We've created reference schematics, equal schematics that you can use for the ATMEGA 168 and the XMEGA 32A4. So if you want to just have like a skeleton where the parts are well defined, or if you want to, take that and copy the parts out into your own schematic, that's perfectly fine. Arduino, obviously, you can just download from their website. So this is our way of making it slightly easier, given that with the Arduino you just get an entire schematic.
Yeah, you're also welcome to use the AT-Tiny
Yeah.
skeleton from Gadget 1
Yeah.
or Gadget 2.
So long as you can justify that you're using a digital interface on these.
Yeah, good luck.
Which, yeah, it's possible. If you use SPI, it's not too bad. Okay, so we're going to do a live demo of XMEGA coding, just so you get an idea, and we're going to do it using a serial interface. This is a BrainLink, and it has Bluetooth over serial, so it's just going to connect to my computer over Bluetooth, but it'll look like standard serial. It has a module in it that just converts regular TTL serial signals to Bluetooth. And then on the computer side, it shows up as a serial port. So I've got WinAVR open, Programmer's Notepad. First let me pull the make file, which I think will, or let me make a new place to put the code. So let's make a folder called XMEGA serial test. I did this last night, so I have all the code here. Okay, and let's get a make file. Put that in there. That's just the standard make file for BrainLink to program it and data on. So like I said, we're using serial. I want to just I'm not interested in rewriting all the serial code from scratch, so I'm just going to use the AppNote driver that AppNote provides. So, that's in this download, and I need usartdriver.h and .c. Those look good. And like I said before, you also need the AVR compiler.h file, because that's referenced by usartdriver.h. All right, if I go into polling control, I can take a look at their example code, and maybe that'll help me get started. So that's task 1. And I'm going to make a very simple thing, which is just a serial interface to blink the LED, turn it on and off on the BrainLink. So, polling is just fine for my application. So let's look at task 1. This I didn't actually look at last night, but I'm sure it's going to be fine. All right, so there's board.h, which we don't need because that's just defined for, I think, an, like a,
That would be your
Next
mini
standard.
gadget.h,
yeah.
you know, that sort of thing. Where are your pins? Where are your LEDs?
Okay, so they have an LED port. They're this is kind of a terrible way to set it, but, and they have a buffer. Oh, that's kind of funny. They're not really setting stuff the way I would expect them. So I'm just gonna close this, make my own. Okay, I'm gonna make a C file. I need to include usart driver.h. And I need int main void.
Do you need AVRA?
Yes. So that's just the overall, like avrio.h just tells the compiler with the information from the make file that this is an ATXMEGA 32 that, you know, basically it maps all the pins, maps all the registers.
Yeah. You want to know what port B is, you have to ask AVRA.
Okay, I'm gonna make some defines for my LED port, which is port B, I think, and then my LED pins, I'm gonna have to look that up. I'm just gonna open my cheat sheet from last night because there's a lot of crap to remember.
Miscellaneous.
So here we go. I'll just So it's a tricolor LED. There are LEDs on pin D0, pin D2, and pin D1. Can everybody see the text okay, or should I try to make it bigger?
Close that bracket.
This?
No, the thing.
Really?
Yes. Okay.
Okay. I'm going to create a 8-bit variable, a character called data, which I will just use to read in characters from the serial port. And then I'm going to set my LED port to be LED port dot gear set. So I'm setting these as outputs, or equals red LED or green LED or blue LED.
The nice thing about dirset is that dirset never actually saves any information, so he can do that. And then if next time he wants to do
I don't
some
even
other
have to do
pin,
it.
he just or equals, yeah.
I'll just do that.
Like there is no dirset, you can't actually read it. It doesn't mean anything. It's just like they created a hardware macro to sort of make it just the code a little bit nicer.
So now I'm going to go into my usart driver.h file because this is where all the functions are. And basically reading this file is how I know what I need to use. So the first thing I need to do is I need to set up my serial port with a bunch of parameters. So, you know, it's a lot of stuff.
Sometimes
I
this
don't
is where
want
you
the-
look at the
Okay. So they've called it usart format set. And they kind of tell you, yeah, they do have, I think there is documentation like that you can auto-create with this to make it look a little bit better. But they have 4 parameters. There's the pointer to the module. There's the character size, which I think is just 8. Parity mode, which I think in this case is no parity. And then 2 stop bits. We don't want 2 stop bits. So I believe I need to do a usart format set. So I'm going to reference, I think, usart D1, which is the serial port on port D, but it's the second one, so it's D1, because the first one is D0. Let me just check if that's right. Yeah. Okay. And then look, all right, so
Where did all that magic come from?
yeah, look at all this. Let me copy these over and explain, because I wouldn't have remembered these either. So USART underscore ch size underscore 8-bit underscore GC basically is a group configuration bit that just sets the USART character size, so the size of each blob of data to 8 bits on the serial port. USART P mode disabled means that parity mode is disabled.
So what's really nice about these is once you figure out what they're called in the compiler,
Yeah.
like retroactive is like, oh yeah, that does make it clear what's going on. But then you have to figure out where to find it. And usually all I do is I find that .h file and I search for things that sound about right.
So on my computer, it's going to be found in C drive, in AVR, AVR, include, AVR, and then under here, IOX, I think 32A4. All right, so if we open that,
And it's long.
yeah, it's
So you
very
just
long.
search for like,
So,
like
okay, there's too much
character
stuff
size.
here. So I would look for USART, and I would keep looking.
F3 maybe? 5,
Okay, so there's a lot of these. So let me just get out of this section, keep going. Okay, this looks like a promising section. So here's a bunch of structs. Like if you wanted, you know, here's the control A register. So you might remember the control A register from random different register modules like ABC, control A, or whatever. Here's the way to access it. Character size. Here it is. And look, it just maps to some random, you know, hex value.
So we get really sad if we see just do 0x03.
Here's parity mode. So you can use disabled, even, or odd.
And hey, look, it supports URDA on the USART. That's nice.
Okay,
These
so
things really can do just about anything you can imagine.
so we've set the baud, we've set the format. Oh, let me. Yeah, okay, that's fine. Now let's set the baud rate. So there's a baud rate set. And unfortunately, the way to set it is not like, let's say you want 115/200. There's a calculation you need to do, which gives you kind of two values. It gives you a select value and a scale factor value. I've already done that calculation, so I know what they are. So what I need to do is I set USART D1, and then if I want a baud rate of 115/200, then I can use these two values. So yeah, I know those came out of nowhere. There's somewhere on Atmel's site is actually a spreadsheet where you can look up where you can ask for a baud rate and it'll give you these values with the minimum % error given your processor speed.
For older 18 megas and 18 tinies, it's a much simpler calculation. So either Atmel literally gives it to you in the data sheet, or people have like macros that just do baud rate set. But ATXMegas are really cool in that they do fractional baud rate generation, and you can actually like do different divisors to get closer and closer to true baud rates. It'd be a lot more flexible. The downside is that it's more complicated. So you could write a baud rate set function, but they don't just give you one. Yeah, I have no idea why.
Okay, one thing I've forgotten to do is I want to set the TX pin to output, and I know that the TX pin, let me just declare it. Undefined TX is pin 7, and undefined RX is pin 6. So I need to also set this out to, and then for the RX pin, I want to be an input because it's reading data in, so I want to use dear clear. Let me just
In this
check
case,
if
the
that's right.
default pin IO control stuff is fine, but you could do funny stuff with it.
And then you also need to enable them as serial port pins. And And so that's something in the driver. So notice enable USART receiver. Because you could actually just enable the receiver and not the transmitter. If you just want to listen and never want to say anything, then you just enable the receiver. So that's USART RX, so that's receive enable. And I only have to give it, I don't have to give this one anything else, I just have to give it which port I'm
And the application note has all this in gory details.
using. Yes.
What is that capital?
I will check. No, oops. All right.
And what you can also do is, you know, you could just steal their example code and modify it to fit your thing.
Yeah.
Probably a little clearer if we not just hack, copy and paste code instead so much.
Brian really needs his brackets closed. Okay, so how do we get data from the serial port? There's if you look, there's a little bit further down, put char and get char. Okay, now it's tempting to just do data equals USART get char, you know, and then this USART D1. The problem is that if you just do this, this is going to run like nonstop basically, and any value that's in that buffer, if it's in the buffer, it's just going to keep giving it to you. Instead, probably what you want to do if you're polling is you want to wait until you get data and then read it once and then wait again until you get more data. So the way to do that is there's a function called isRxComplete. So is receive complete. This basically just checks, is that the right one to use?
Is there a key
Check.
here?
Yeah. So what you can do is you can make a while loop that as long as Rx is not complete, it just hangs out in the while loop and does nothing at all. So you can see how this is horribly inefficient because you're just burning all this time just checking this over and over again. And this is why interrupt-based methods are usually better.
This is the equivalent in like C code of KB hit.
Is
on, like
RX.
a regular computer. Like there is get C, there's put C, and there's KB hit. Where you're like, did anyone hit the button on the keyboard? If so, we want to read the character, otherwise we don't read it.
So in this loop, we're going to wait until we've gotten some data, we've gotten a chunk, a byte of data, then we're going to read it in. I like to transmit it out again so that you can see, especially when I'm just testing, I like to just see that it's actually receiving and that I'm transmitting. So the first, if I've just written a serial program, the first thing I do is I have one where I get data and then send the same data back just to make sure it's working.
So a remote echo program basically.
So there it is. So you start put char to you start D1 and then send out data.
Should we see the loop?
Yeah. So I'm going to save this. And because my make file is already configured to compile things with the name of main firmware, I'm just going to call it main firmware. It's really lazy.
Back. These are lectures, it's in lectures.
All right, main firmware.c. Tell me what mistakes I made. Okay.
Sorry, is complete. What's it actually
What's
called?
the declaration?
So what's it actually called?
Yeah, so I made a mistake in how I called it. Is Rx complete? Probably just
RX is both.
Rx is capitalized. So the X is capitalized. Okay, I'm going to set this in bootloader mode. So this has a bootloader. What that means is, unlike your mini gadgets, it doesn't require an ISP. It has a little program that hangs out way at the top of its memory stack, And it checks if one of the pins is grounded on boot. And if so, this is like the equivalent of having a button pushed down on boot. If so, it goes into a bootloader mode. And the bootloader basically allows the rest of the program, once it's in that mode, any data that comes in over serial, it says, this is program data, I'm gonna make a program out of this, and I'm gonna reprogram the flash memory. So that's what it's doing. It's in bootloader mode now. Bootloader mode is indicated by a blue LED. And so when I hit Tools, Make Program, if I've configured the COM port correctly, and if everything's working, it will flash the LED while programming. All right. So now it's in regular mode, and the LED is actually on. It's kind of hard to tell because it's just green, but the red one is on and the blue one's on. They're just dimmer. Because this LED is inverted, and when I set those all to outputs, they were default low, and so all the LEDs turned off. But that's okay. It's minor. Let's just check if the serial is working. So I use a terminal program called RealTerm, which is freeware.
You're in Windows, you want RealTerm.
RealTerm is nice. You have a lot of options. So I set the baud rate to 115.2. Oops. Port scan. And I know that I'm on port 45. So if I open it, it takes a little while because it's Bluetooth. If I type R, G, so I'm just sending data, and it is sending it back to me. So yay, my program's working.
Your display.
Right.
Just check the local echoes.
I think there's a local echo somewhere, but I know.
Probably that.
The nice thing about RealTerm is you can send in like hex. You don't have to. You can also look in hex. So if you ever want to find out what the code for lowercase g is 67.
Yeah, it's much better. Honestly, I like it better than a lot of Linux options. And if you're on a Mac, well, you can get a virtual machine and run RealTerm. It's pretty nice. And this hasn't been updated in years, but it just is very flexible. And let's say your baud calculations were wrong and you just can't figure it out. This will actually let you just be like, you know what, I want 112,000. You just can type it in, and as long as your hardware supports it, it'll do it. And you get a lot more flexibility over this stuff. Whereas Hyperterminal, first it wants to know your area code for some reason, and then you get your 4 choices of baud rate, and you have no choices other than that. So RealTerm is very flexible. The only way to get more flexibility is to actually write your own serial terminal program, at least that I've seen.
Do you want to do the mini gadget?
Sure.
Okay, because we got 10 minutes, so
Yeah.
I'm not gonna.
All right, so that is, I'm going to just find the code.
Yeah.
So just in the interest of showing you some other stuff, we're also going to give you, so that's just the ATML code that Tom downloaded. He obviously wrote a little bit of code, but if you copied their first example, it would work the same. For those of you who are sticking with the ATTiny, just open the bladder.c.
So yeah, if you want to stick with the ATTiny, not even the ATMEGA, but the tiny, or if you want to make your current gadget or your mini gadget have a serial port.
This is how you can do it. It's actually a lot more complicated than it looks. I don't think, for instance, we actually need sleep. I don't think we need atomic, standard lib, or string. Just what ends up happening when I'm writing code is I have all this stuff, and I just keep adding these header files. They usually don't harm me to leave them in, but then we delete a bunch of functionality for an example, and we just sort of stick it. So if you look into AVR libc, which is, you just Google it and look at it, it has a lot of functionality. So for instance, if you would like something like printf, you can have it. You just have to set up a stream. And this ends up looking a lot like what you do on like a Linux computer. They explain it in gory detail. What you have to do is you have to give it a a way to send characters, and then if you want to, you send them a way to receive characters. Here, since I'm only writing, I've only done the add char, but if you did set up read write, you could also send and receive. It's pretty straightforward. And then what you have is we have the main function, and then I'm just initializing a software URL. Here I do standard out equals my standard out. If I just called this standard out, printf would work. So printf will always print to standard out. But I could have also done this. Let's see. And that will also work. So there are these sort of basically library support to give you things like on a regular computer, like printf, the string library, like it has a whole bunch of that sort of old crufty C stuff that it's convenient. But basically all this is going to do is printf, banana, and then delay. So we could have done this exact same thing. If all of this was hiding out in a library.c and .h, you'd never see it. If this was in something called, a function called setup, you'd never see it. We had another thing called the loop here, right? You can make this look very pretty if you wanted. Maybe change the fonts on programmers' notepad to be blue. But basically that's all there is to it. What's actually going on, if you're curious, is we've got software.c and .h. Where all we've done is, here we define some pins. So if, for instance, you want to have your software on different pins, it's fine, just change them. Here we've got a baud rate. This is software UART. It's on a slow microcontroller, so you're not going to get 115, 200. I think you can go up to 38, 400, but slow is good. If you wanted to have more software UART, so you can have more. And then what we're doing is there's a get char, a put char, there's add char, print string, KB hit, that's very handy for do I have any data in my buffers. And then what actually is happening is we're using a timer. So instead of doing it to blink software PWM, we set up a timer at around 9600 baud, and we just look and see, is there data on my serial port? And if there is data, let's go find the timer function. So if the serial port has no data on it, we're just hanging out, but then we suddenly see data, then we're going to start capturing the bits. And we start at mask, we start at the first bit, and then we just keep capturing bits until we're up to the stop mask, which I think is 10. And then once we get to the stop mask, if we get a stop mask, then we're going to push our 8 bits of actual data into a buffer. And same thing with the transmit. If we actually have something to transmit, and that transmit happens to be high, then we output a high on that pin. Otherwise, we output low, and then we just keep shifting through the bits on this buffer until we're out of bits.
So this is actually, what this is doing is because your ATTiny doesn't really have a hardware serial port, or it has sort of a pseudo one, this is doing in code what a lot of the hardware would be doing automatically on an XMEGA or even on an ATMEGA. So that's why it's so complicated and why there's all this bit shifting, and why you can only go at 38 and 400 bits per second.
Now, there actually is a serial port on your ATTiny. It's the USART, it's also used for SPI. This is really handy if, for instance, you wanted to talk SPI to your accelerometer or something else, but then you say, well, gee, what would make my life 100 times easier is if for development, for debugging this thing, I can talk to it and figure out what's going on. So that what you could do is like, okay, every time my gadget turns on, it'll send something to the serial port. And then like you're working on it, you're doing some code, and you're like, every time I do this, it resets. And I know it reset because it's telling me over the serial port that it just reset. And this is sort of, this is the printf style of debugging, which is, a couple orders below JTAG style debugging, but it's still better than nothing.
So even if you didn't intentionally put this on, it's likely to be on your ISP header, and unless you've overloaded those pins, you probably just have it.
Yeah. So
even on your gadget.
So for gadget 1, you guys could use this code, plug in these pins. You just put the TX and RX to your WISO and MOSI pins, and you should be able to have like a little mini UART to talk to yourself. And it'll help you a lot. Like, let's say you're getting a sensor value, and you're trying to figure out whether you should have a red unhappy LED or a blue, happy LED, and you don't know whether a value on your sense resistor of 170 or 62 is the right value. It might make your life a lot easier to just read in the analog value and then just tell yourself what it is. Because this is printf. So, for instance, if we had a analog read sensor 2, so we'll say value sensor 2, and then what we can do is %D or %X. And just every time it prints the data, it's also going to print your sensor value. And you'll know what your sensor value is as opposed to guessing. So that's something we usually give you guys on the mini gadgets. This mini gadget we forgot, but here it is. Here's serial on your mini gadget. And also for your gadget ones. As long as you have your ISP header and you didn't overload all of the pins and like completely take away any extra I/O, you can reconfigure it as a serial port. All right, any questions on software serial? I think we'll upload this somewhere.
Yeah. Yeah, so we have a bunch of stuff to send to you today, like this, the reference schematics, and also information about the fuses.
And it's basically going to end up on the website, so look there. The email will simply say, we put it on the website.
Any questions about any of this stuff, or any upcoming homeworks, or anything else?
We get to look at all kinds of exciting Gadget 2 use cases today. All right.
Okay.
You want the MPD or MPU? 6100? IMU? MPU or MPD 6100?
You always stop us for.
Yes,
Brent.
6100. The InventSense one? Yeah. That is the cheapest, best.